Hey guys, my name is Cadet Sharif.
And I'm Cadet Zua, and today we're going to be looking at an MA 103 Complete T Review.
Whether you're studying for a WPR individually or you're studying for the entire T, this guide is for you. If you're on an individual WPR, skip to the section. If you're here for the T, stick with us for the entire ride. It's going to be a good time. We're going to help you get that A+.
Sounds like a plan. Let's get into it. Hey guys, we're going to jump right into it. We're going to be using AY24-1 WPR1 version A, version alpha. We're looking at question 1 here. It's 45 points, 5 parts. It's a whopper right there. The question's going to be right here. So the number of operational M4 rifles in the arms room during summer training can be represented by the model below. For us, I have it written right above us. On June 1st, 2023, there's 1,600 operational M4s in the arms room. So that's our R0 initial right there. Where R sub N is the number of operational M4 rifles in the arms room, N weeks after June 1st. Okay, so for part A, I need to use the DDS model to estimate the number of operational rifles on 15 June, 2 weeks later, when the yearlings start Buckner. Okay, so for this one, the first thing I want to do is I want to isolate for my N value, right? So my R sub N, I want to get that alone so I can find like a generic equation. So the first thing I'm going to do is I'm going to add R sub N minus 1 to the right-hand side of the equation here. What that's going to look like is I'm going to have R sub N is equal to negative 0.25 R sub N minus 1 plus 0.2 R sub N minus 1 plus 2 plus R sub N minus 1. Okay, so the next thing I can do is I want to make sure I get all my like terms. So my like term is going to be the R sub N minus 1 variable that I have on the right-hand side. I'm going to make sure those all go together here. So I can add my negative 0.25 to my 0.2, and I'm going to get negative 0.05 R sub N minus 1 plus my R sub N minus 1 plus 2. And really, this R sub N minus 1 just has a 1 in front of it because it's the whole R sub N minus 1. So when we add those together, I'm going to have positive, so this is all going to be equal to R sub N. I'm going to have positive 0.95 R sub N minus 1 plus 2. All right, so that's going to be like our generic equation. That's the first step on part A. So the next thing I want to do is see how many rifles are going to be after 2 weeks, right? So the first thing I'm going to do is I'm going to have R sub of 1. So when N equals 1, when I plug in for N equals 1, I get N minus 1 is 0. So we know R naught is 1,600. So what that's going to look like when I plug in for R sub 1 is going to be 0.95 times 1,600, right? Because we know that R of 0, so R naught is 1,600. Plus 2. Use your calculator on this one. When you use your calculator, you can get that to be equal 1,522. So you have 1,522 rifles in the arms room after 1 week. So for the second week, I'm going to plug in for R of 2. And we're going to do the same thing we did earlier, where we're going to do 2 minus 1, right? 2 minus 1, N equals 2. That's going to get us 1, so we know that's 1,522. So for this one, I'm going to get 0.95 1522 plus 2. Use our calculator. Again, make sure you use a calculator on the math stuff. You get 1447.9. And for that, you're going to want to round, right? You can't have 0.9 rifles. We're going to round, and we're going to get 1448. Double underline that. Don't forget your units. That's our final answer for part A. We're going to continue on into part B here. So part B says, if this situation continues indefinitely, how many operational rifles will we have in the arms room long term? Okay, so what that's saying is, if this continues indefinitely, what are we going to get? So this is written in the form. You should make sure you have this next stuff on your note sheet. This is written in the form P sub N equals A, the coefficient, 90.95, of P sub N minus 1 plus D. And we can actually derive an equation. That's a big word. We're actually going to get an equation, add this to your note sheet. We know that P star is equal to D divided by 1 minus A when A is not equal to 1. Okay? So in order to solve this question, we know that our D here is 2. So we're going to plug that in. 2. And we know that our A here is 0.95. So we're going to do 1 minus 0.95. And that's going to be our P star, which tells us the equilibrium point. So this is going to be the equation for equilibrium. Have that on your note sheet. Plug this into your calculator. It's going to equal 40. Double underline. On to part C. All right, so getting into part C here, we're asked to classify our equilibrium point. So when we're looking at that, what we're going to say here is something just to know for your notes, maybe just general knowledge. The equilibrium point classification is when A falls between -1 and 1. Another way to write that is if the absolute value of A is less than 1. Those are basically saying the same thing. So what we're going to do is just going to plug in our A. A equals 0.95. So 0.95 does in fact fall between -1 and 1, which means that we can classify it as attracting. So we're going to call that A-T-T-R-A-C. Double underline. We're good to go. All right, so keep going on this problem 1. We're looking at part D here. We're asked to determine the particular analytic solution for this DDS. So for this one, this is another one for the note sheet. We're going to want to remember the formula that P sub n is equal to P star plus A to the n minus I times P sub I minus P star. Okay. Make sure that you have that on your note sheet. So basically, you're going to plug and chug on this one. We know that P star is 40. We know that A is 0.95. Right? And then we know that I, so our I value, right, when we said P naught, that's our initial value, I for initial, is 0. So I is 0. So we're going to do n minus 0, which is just n. And then we're going to multiply that by our initial minus our final. So our final. So we're going to have 1600 minus 40. And this is all going to be equal to our P sub n. You're just going to basically plug this in. You don't need to solve because you can't solve for n. So now you know that the closed form, so the particular analytic solution, is going to be 40 plus 0.95 to the n times 1560. Double underline. You're good to go. I'm swearing this is the last try. Okay. All right, guys. We're going to jump into part E finally on this problem. It's going to ask us how many weeks it will take for the number of operational M4 rifles in the arms room to fall below 1,000, which is apparently the minimum required to conduct training. Okay. So for this, we're going to say that P of n, that's the number of rifles. We're going to set that equal to 999 because that's 1 below 1,000. That's the first integer below 1,000. So when does it finally drop below? We're going to set that equal to the rest of our equation, plus 0.95n times 1560. And then I'm going to solve for n, because n is the number of weeks, right? So when I'm using n, that's what I'm going to try and get to. The first thing I want to do is subtract 40. So I'm going to get 959 equals 0.95 to the n times 1560. And then I'm going to divide by 1560 on both sides. 1560. And I'm going to get 0.614 equals 0.95 to the n. Okay? So when you take out your calculator, right, we're going to use the logarithm. Remember, we're going to have log base 0.95. Let me fix that. 0.95 of 0.614 equals n. Write in your calculator again, you're going to get that n equals 9.49 weeks Do not forget your units. Final answer, sorry for the handwriting. You're good to go. All right, we're gonna go into number 2 now, same WPR version alpha. Should have about 4 parts. This is technically part A, B, but A is parts 1 through 3, so it's really 4 parts. Strontium-90 has a half-life of 29 years and is used as a power source for space vehicles, linear discrete dynamical system below, which I put right there. Models the number of grams on board recent space vehicles. The space vehicle only has a capacity to launch with 20 grams on board. So, yeah, I guess that's how much the S naught equals. So that's what I have. S naught equals that. Yeah, so on part A, we're going to say for the following scenarios, 1 through 3, use one word to describe the long-term behavior of the quantity of strontium-90 on board the space vehicle over time, then use a limit notation to describe the long-term behavior. Okay, so for number 1, it says that the resupply is 5 grams, therefore we have D equals 5. To do one of these equations, we want to make sure that we're using this equation, okay? Have that on your note sheet. Super important if you don't have it already. What we're going to do is we know that S naught is equal to 20, right? We already have that. S naught equals 20. We also know that D equals 5, and so we're going to plug this into the equation to find our S star instead of P star, same thing. So S star equals 5 for D over 1 minus 0.5. We get that from up here. That's the A value, remember, from up above. And then use your calculator, find out that equals 10. It's converging. We know that because A is between 1 and -1, so that's already given every time. To do the limit equation, though, I'm going to say as the limit, as n approaches infinity of S sub n, so that is equal to S star, right? Oh, sorry. S star, because we're trying to find like what it gets to when you put an infinity, right? An equilibrium point. And we know that is 10. So that's going to be your answer for that one. Easy peasy. Going on to the second equation, where we have the second question there, where D equals 20. Again, we're going to do the same thing. So we know D, we're going to use our equation. So we're going to say that S star equals 20 over 1 minus 0.5. Use your calculator. Equals 40. Again, so A is between -1 and 1, so we know it's converging. So make sure you write that down, actually. Forgot that in the last one. Write that down. Converging, that's the one word that we're using. And then to describe it in limit notation, again, we're going to say the limit as n approaches infinity of S sub n, that is equal to S star, again, the equilibrium, is equal to 40. Double underline. Answer. Part 3 for number 8. We're getting a lot of reps in for this one, apparently. Really want to make sure you know this. We're going to say that D is equal to 10. We're going to plug it in again. S star equals 10 over 1 minus 0.5. Surprise, surprise. Still converges. A is still between -1 and 1. So I say it converges. Write that down. And then put that in your calculator, right? We know that equals 20. To do the limit, we're going to say again, the limit as n approaches infinity of S sub n equal to S star, which is therefore equal to 20. Make sure you guys are using units for all of these. The units are going to be grams. I forgot to write that on the previous ones. Do not forget those units. Always label everything like we had in the last problem. Don't forget that. So grams for this one. Don't lose that point. Okay, so part B for this one, kind of tricky. We're just going to be going in reverse pretty much. So it says, what is the minimum quantity of strontium-90 that NASA could send on each resupply if the space vehicle must maintain at least 8.24 grams on board to operate indefinitely? So basically what I'm saying here is what is an equilibrium value, right? So my equilibrium value is going to be 8.24. So for this, I'm going to say that my S star equals 8.24. Now, I say that because it's saying if I have 8.24, how can I operate indefinitely, right? So that's what we're saying. Like the previous sections 1 through 3 on that one, they're all operating indefinitely at that D amount. So for this one, we're going to try and find the D amount, how much you're going to send every single time. So we're going to set this up using our same equation. We're saying 8.24 equals D, right? That's our unknown, over 1 minus 0.5. Little calculator, little algebra. This is 1/2. Multiply it up. So you're basically just dividing this by 2, and you're going to get 4.12. So D equals 4.12 grams. Grams. Do not forget your units. That's number B. All right, so we're going to get into the next questions with Solar.
All right, time for problem number 3 of WPR1. Let's do it. So I'm going to read it out loud first, and then we're going to go right into it. So, plot the linear discrete dynamical system on the graph provided for all values of n 0, 1, 2, 3, 4, and describe the long-term behavior of the system using one word. All right, so here's our equation right there, and here's our graph. So to start off, we are given that the initial value p sub 0 is 1. So when we look at our graph, we can immediately put that p sub 0 is going to be 1 over here. We're labeling it 0, 1, 2, 3, 4. Same on the y-axis. So to find p sub 1, all we need to do is p sub 1 equals negative p sub 0 plus 4. And the reason we put p sub 0 here is because our equation says that the previous term is going to be negated and then 4 is going to be added. So that's why we put it here. And if we look up, we know that p sub 0 is 1, so we get p sub 1 equals 3. So I'm going to put that on our graph. So on 1, we'll go up to 3. And then we just continue the same process for the rest of them. So for p sub 2, it's going to equal negative p sub 1 plus 4. And p sub 1 is 3, so that's going to give us negative 3 plus 4, which gives us 1. And I'll put that over there. So as you can kind of see, we're getting a pattern showing. It's going up, down, up, down. Now I'm going to do p sub 3 and p sub 4 together to save some time. Let's do that. So we got that p sub 2 is going to be 1, so it's going to be negative 1 plus 4. That's going to give us 3. And then p sub 4, following the pattern, is going to give us 1. So let's put that there. So p sub 3 is 3. And p sub 4 is going to be 1 over there. Now that we have that graph set up, let's classify it using one word. So looking at the graph, can we see what type of behavior is happening? It's going up, down, up, down, up, down, up, down. And no matter how far we go, it's going to keep oscillating between the two. So we know that it's diverging because it never joins in together. So our word is diverging. On to the next part. All right, time for problem number 4. So create an arithmetic sequence and write the first 4 terms below. Write the DDS it corresponds to. Provide the particular analytic closed form solution for the DDS that you generated. So I'm going to start off with writing an arithmetic sequence. So remember, arithmetic means we're adding or subtracting in our pattern, and geometric, if it asks you for a geometric sequence, it would ask for multiplying or dividing. So since we're an arithmetic sequence, I'm going to start with 10, and I'm just going to go by subtracting by 2. So I'm going to go 10, 8, 6, 4, and I'll end right there. So you can pick whatever you want to do if the WPR asks you. I just decided to subtract by 2. From here, I'm going to create the DDS, I guess, for this sequence right here. So I'm going to do p sub n is equal to our previous value minus 2. So p sub n minus 1 minus 2. And if we think about it, the next value is going to equal the previous value minus 2, right? 8 is, this value over here is going to equal 10 minus 2. So that's where we're doing the previous value subtraction. And now we just need our initial value, which is p sub 0. I'm going to put in 10 because that's what I started my sequence at. You put in whatever you started your sequence at. Now for part C, we need to find the particular analytic closed form solution. So if you remember, for arithmetic sequences, you will have this on your note sheet, or at least I hope you do. It's P sub n equals P sub 0, our initial value, plus our D value times n. Now remember, our D value is this term over here. If you want to scroll back to Zuhat's portion where he explains the equation, or look at your note sheet, you have your D value. And then we have P sub 0 here. So we can write it as P sub n equals 10 plus, or in our case, minus, because our D value is negative. So I'm going to put minus 2 times n. And there we go. We have another form of our equation that describes this sequence up here. Let's move on to the next problem. All right, problem number 5. Answer the following prompts based on the DDS presented below. So here's my DDS up here. It's 4p sub n squared minus 1 over 175, all multiplied by this over here. I'll let you read that by yourself. The first question is, how many equilibrium values S does this DDS have? And explain how you arrived at this conclusion. So remember, when you're finding the equilibrium values, you're going to set p sub n equal to p sub n minus 1. So you're going to use p star for both of them. But before we actually dive into that for the later part of this question, you can kind of eyeball this question and see how many points you're getting. Because the highest power in this equation is going to be to the third. Now you might be wondering, well, I only see a squared up there. But the reason is when you distribute this over, you're going to get a trinomial because the p squared is going to get multiplied by the p over here, or the p stars are going to multiply with each other, and you're going to get p star cubed. So since you have a trinomial, you're going to have 3 equilibrium points, and that's your reasoning. So for part B, now we're going to calculate the equilibrium points for this equation. So to start off, we're going to set all the p sub n's equal to the p sub n minus 1. So we're going to use p star. So p star equals 4p star squared over 175 times 1 minus p star instead of p sub n minus 1 over 400. So we have that over there. We've replaced everything. Now what I want you guys to do is distribute this over. So it becomes, this 4p goes over here with the 1, so it just becomes 4p star squared over 175, and then subtracted with, this becomes cubed, that's where we get our trinomial, 4p star cubed, and then we're going to multiply our two denominators together, 175 and 400. I'm just going to simplify it to 70,000, and there we go. And that's all going to equal p star, but if we set it equal to 0, we can move our p star to this side, so it'd be minus p star. So just to reiterate that again, you can just move this term to that side, which is what I did over here. And now we have a trinomial over here. So the next step we're going to do is factor out a p star. So I'll do p star is equal, or p star multiplied by 4p star. It's no longer squared because we pulled out a p star over 175 minus 4p star. This cube becomes a square because we pulled one out over our 70,000. And then this p star just becomes a 1 because we pulled out the p star, and that's all equal to 0. So over here we can already see that we found our first 0 because we just have a variable, or our p star, multiplied by everything else. So that means it's equal to 0. You just set that equal to 0. Now we need to find the p star values for here, and we know we only have 2 more because of the way we answered the first part of the question. And the way you do this, you can identify it's a quadratic, it has a squared value, it has a normal value, and it just has a constant. So put that into polysolve in your calculator, and you will get 50 and 350 as the solutions for this one over here. So remember, you use polysolve on your calculator. You could use the quadratic formula if you wanted, but yeah. And then we also have our 0 over here, which we got from this. So you have 3 different solutions. Now for the next part of the question, it says, what is the value of p sub 50? So the 50th iteration of this equation. Now if we look on the top, we have p sub 41 equals 50. And we also know that once we reach a certain point over here, we're just going to stay at 50 because it's an equilibrium value. We're no longer going to go bigger. But you might be wondering, why'd you pick 50 instead of 350 or 0? Because couldn't the equation just stop at 0 too? Because you're saying it's an equilibrium point. So is 350. The reason is because P sub 41 is 50. So if we're going naturally from 41 onwards, if we plug in 42, we're going to stay at 50 because it's an equilibrium point. And because of that, we're going to go 43, it's 50, 44 is 50. So we're never actually going to be at 350 or 0. We're really only going to be at 50. So it's the only one that actually makes sense, which is why we're going to pick P sub 50 is going to equal 50, because that's the most reasonable equilibrium point we got. So I hope that helped. On to the next question. All right, we're finally on the last problem of this WPR. Question number 6. If you're tired, we're almost at the finish line. So without further ado, I'm going to read through it. It's a really long one, so bear with me. You are the battalion medical officer and received the additional duty of field sanitation officer for your battalion's training cycle at Fort Irwin. On the 10th of April, your medics tested all the water buffaloes and only found one contaminated. The medics tested the water over 4 days to figure out how fast the bacteria is growing, and they gave you the following report. So I'm going to paste that up here in post-processing. You can take a look at the values. Using a technique from your field sanitation course to bring the concentration below the allowable limits of 0.65 ppm or parts per million, you instructed your medics to treat the water with chlorine. Unfortunately, you're limited in how much chlorine can be added to drinking water, and the chlorine can only lower the contamination by 0.156 ppm per day. Perform the transform step of the USMA mathematical modeling process to build a DDS using the contamination data and the quantity of water you remove from the water buffalo daily to predict the future contamination starting on the 14th of April. So, to start off, part A, we're going to define our variables. I'm only going to define P sub n with words. I'm not going to write it down just because I don't want to take your time like that. And P sub n is our only variable for this. So, P sub n is going to be the number of contamination parts in the water buffalo n days after April 13th. Make sure you take note of how the problem says you start on April 14th, the first day. So the first day is going to be April 14th. So make sure you take a note, read your problem. You don't want to get points docked off that. So that's part A. It's the number of contamination parts in the water n days after April 13th. Now part B is going to give you a multiple choice selection. I'm going to put the options up here, and it says, one of the necessary assumptions to make in modeling the scenario as a DDS is to choose the rate of change of contamination concentration. Choose the most appropriate assumption from the list below and justify why you chose this assumption. There are too many words in this question. But I assure you, on the WPRT, please read it so you don't miss over critical information. So looking at all the options, we got number 2 is going to be the correct answer, and I'm going to justify it for you. So over here, I'm going to just put that number 2. Number 2 says the contamination concentration is increasing 6.25% daily. And the way you check it out in your justification part is if you look at your table, hopefully I edited it back here, if you do the difference between two, so let's do between April 11th and April 10th, April 11th gives us 0.85, and April 10th gives us 0.8. And if we divide those two by each other, we get 1.0625. Something like that. You can plug that into your calculator to make sure. But as you can see, we have a 6.25 increase daily, and if you follow the table, you'll see that same pattern trend. So you want to test whatever they ask you for all of them. I'm just going to save your time and tell you it's number 2, but be sure to thoroughly check all of them. Now here's where the magic happens. We're going to take our 6.25%. We're going to take the amount of chlorine we add each day, and we're going to create a DDS model. So, starting off, P sub n. We always define P sub n. That's what we're looking for. The amount of contamination we have after April 13th is going to equal our growth rate, our growth rate, which is 6.25%, times our old amount, but we're also going to take away the amount of particulate killed by, or the amount of parts per million killed by the chlorine. So that didn't make sense. Let's break it down a bit more. So we know we're growing by 1.0625%. So that's what I'm going to put multiplied by our previous value, because remember, if we have a certain amount the day before and we're going up by 6.25%, we're going to multiply that by 1.0625. So that gives us our growth in bacteria, but remember, we're also going to subtract chlorine from it, or the amount that chlorine kills. And if we look at our problem, we can see that chlorine can limit the contamination or lower it by 0.156. So we're going to do minus 0.156. And that's going to be our equation right there. Again, we have 6.25% growth. That's the natural growth rate of contamination we found from our table by using the slope formula. And then, or the rate of change formula on our table. And then we multiplied that by our previous value, but then we subtracted 0.156 parts per million because chlorine is getting rid of it. And then we have our P of 0, give it its initial value, which is going to equal 0.960 because we are starting after the 13th of April. So I hope that helped. Now we're going to move on to the outro.
Oh, yeah. So I actually just got an email from the course director. Apparently they're changing the entire MA 103 course. So I hope this video helped, improve your general knowledge and maybe prepared you for the T. If not, really sorry. Blame the math department. Thanks. Bye.